Okay, so we're in 3.2 now, and just quick review. In 3.1, we introduced the basic basic concepts and terms for symbolic logic. Talked about what statements were, and we talked about some logical connectives like and, or, and not, or as we call them in logic, conjunctions, disjunctions, and negations. And we didn't do a whole lot of analysis with those things. It was more just kind of getting used to the terms. But in 3.2, we want to start looking at working with those concepts, getting a little more hands-on than we're able to in 3.1. So most of the work we do here is going to be working with statements in their symbolic form, and not quite so much with explicit examples of statements. So you'll see what I mean as we kind of move through this. First thing we need to talk about is a truth table. So when we're talking about determining a truth value for a compound statement, something like P and Q, whatever P and Q happen to be, what we tend to want to do is determine all possible combinations of the truth values of P and Q. And in a case where we have these two component statements, P and Q, there's a total of 4 possible combinations. P and Q can either both be true, P can be true and Q can be false, P can be false and Q can be true, or they could both be false. Those are the only 4 possible combinations of truth values for the statements P and Q, whatever P and Q happen to be. And notice I'm not giving explicit examples of what P and Q are. It's just looking at those combinations. For all of those possible combinations, what are the possible truth values of the statement P and Q? Well, that's what a truth table analyzes. So this is what a truth table looks like. We want to analyze the compound statement P and Q, the conjunction P and Q, which symbolically we know looks like this: P, the little up arrow symbol, and then the Q. The way that we want to go about this is we want to create columns in our table, one column for every component statement in that compound statement. So a column for P and a column for Q. And then what we want to do is build up any compound statements that show up in the overall compound statement. Right now, the only compound statement is P and Q, but we're going to look at some more complex examples later on. So starting with this, these 2 columns are going to carry the possible truth values of P and Q so that we get all 4 of those combinations that I mentioned. And again, P could be true and Q could be true. P can be true and Q can be false. P can be false, Q can be true. P can be false, Q can be false. Those are all possible combinations. Now, what does it take for a conjunction to be true, and what does it take for a conjunction to be false? Well, the truth value of the statement P and Q can only be true if both P and Q are simultaneously true. That's what the and is implying. This statement is only true if P is true and Q is true as well. So in our first row of our truth table, where P is assumed to be true and Q is assumed to be true, in this case P and Q would also be true, because that's what it takes for a conjunction to be true. However, you'll notice in all 3 of the other cases, the statement P and Q turns out to be false, because even if one of the statements is true, in all 3 of these other cases, at least one of the other statements is false. And in a conjunction, you need everything to be true for the conjunction to be true. So that's why the rest of these are coming out false. Okay? Here's an example. Let's let P represent the statement 5 plus 6 equals 11, and Q represent the statement -1 is less than -2. What we want to do is determine the truth value of P and Q. So in this case, what is the truth value of P? Well, P is true because 5 plus 6 is equal to 11. That's easy to verify. We know that's true. What about Q? Is Q true or is Q false? Well, Q is a statement that -1 is less than -2. That's false. -1 is not less than -2. -1 is greater than -2. So that means that we have a true statement and a false statement, and we're forming a conjunction from one of those. In our truth table, we see that a conjunction of a true statement and a false statement is false. So that implies a truth value of false, which we just write F for that. Okay. Let's look at some other connectives. What about a truth value or a truth table for the disjunction? That's the logical connection or. Same idea. I want to determine the truth table for the statement P or Q, whatever P and Q happen to be. And again, we want to consider all possible combinations of truth values for P and Q. So for that reason, the first two columns of this table will look identical to the first two columns of the previous table because all those are doing is considering the possible combinations of P and Q. Next up, we want to determine what it takes for a disjunction to be true and what it takes for a disjunction to be false. The disjunction, using the term or, will always come out true as long as at least one of the two component statements is true. So if they're both true, great, then the disjunction is true. If P is true and Q is false, at least one of those statements is true, so the or statement or the disjunction is true. If P is false and Q is false, if P is false and Q is true, then at least one of those statements, in this case Q, is true, making the entire compound statement true. However, if they are both false, then we cannot say that at least one of them is true, and so that's the only time that this disjunction comes out to be false. And that explains where we're getting true, 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 false from those different combinations. You may notice that in comparing these two tables, it seems like conjunctions are false most of the time, if we consider each of these rows equally likely, and then disjunctions seem to be true most of the time. But neither of them are always true or always false. So in this case, let's take a look at an example. Same statements as before. P and Q represent the statements 5 plus 6 equals 11 for P, -1 is less than -2 for Q. And now we want to determine the truth value of P or Q. That's how we read this. Well, again, it only takes one of these two statements, at least one of them, to be true to make the entire disjunction true. And because P is true, it doesn't matter what Q is. We know that we have a true statement. Notice this would correspond to the second row of this table where P is true, Q is false, and the disjunction comes out true. All right. The other main logical connective that we talked about was the negation, not P. So we need a truth table for this statement, not P. Now notice in this case, I don't have a P and a Q. I only have one statement, one component statement that's being used here. So I'm going to have a smaller table because there's only two possibilities for the truth value of P. It's either true or it's false. We don't have to look at combinations of P with, another statement. So what do we know about the negation? Well, the negation of a logical statement is always has a different truth value than the original statement. That means if P is true, then its negation must be false. If P is false, then its negation must be true. Okay, so let's consider this example. Different statement, let P be the statement the earth is flat. Determine the truth value of not P. Shockingly, there's some people who want to debate this fact, even in these days, that they want to say that the earth is flat. There's a whole flat earth society out there. They are blatantly wrong. There's no truth to that. So this statement, P, is false to begin with. That implies that we're looking at the second row of this truth table. When P is false, not P must be true. So that means that we're looking at a negation or not P, which is true, and we would write T for that. Okay? So, let's take a look at a more complicated statement. This one involves three component statements. Notice we're not stating what P and Q are, we're just giving their truth value. So let's suppose that P and Q are some logical statements and that both of them have true as their truth values. And let's say that R is a third logical statement which is false. What we want to do is determine the truth value of this compound statement here. Now, as we'll see pretty soon, if I were to make a truth value or a truth table for this compound statement, it would have to have 8 rows. and it takes a little while to make those. We're going to make some later. But the truth table, making an entire truth table, is overkill for a problem like this. And to see why, let's return to the work that we did here. So for example, my first example that I did, we had this truth table with 4 rows, giving us all possible cases for the conjunction P and Q. But in the example below it, we were given a specific statement for P and a specific statement for Q, for which we could determine their truth values. One was true, one was false. That meant to determine the truth value of P and Q, we only needed one of those 4 rows in that truth table, meaning the other 3 rows were unnecessary to solve this one problem. So something similar will be true in this example. If I want to determine the truth value of this compound statement, it would be completely unnecessary to make a truth table with all 8 rows if I only needed one of those rows to begin with. So in a case like this, we don't go that far. We just work with what we have. If P and Q are both true statements, and if R is a false statement, let's consider what would happen if I substituted the truth values in for each one of these component statements. So P or not Q, see that that's in parentheses, and R. So now let me think about if I put in the truth values for each one of these. P is a true statement according to what we're given. So I'm going to write true for that. Or not Q. Q is another true statement according to what we're told. So this is not true. Notice I'm substituting T, the truth value, in for the Q. And R, what do we know about R? We're told that R is a false statement, so this is false. Okay? Now, let's do this like you would order of operations. Let's deal with the things in the parentheses first. And remember this for a matter of convention. Not convention, this is like order of operations when working with logic. If it's coming down to dealing with a negation, or dealing with either an and or an or connective, always do the negation first. So I want to deal with that negation. I'm going to treat this like an arithmetic problem, so I'm going to use this equals sign, and we'll actually give a better definition for what this equals sign represents at the end of this section. But for now, I'm going to just think of it like, one statement equals another. What does a negation do to a statement? Well, if the original statement was true, then the negation of that statement would be false. So saying not true is the same thing as saying false. So notice the only thing I've done is I've evaluated this negation here. Everything else is looking the same. Okay? Next up, we need to work with what's in parentheses before we deal with the things outside of parentheses. True or false. Because this is the logical connective or, it's a disjunction. In our truth table for disjunction, if the first statement is true and the second statement is false, then the disjunction is true. So true or false evaluates to true. Okay. Then finally, notice I've worked out what's in the parentheses, so I don't need the parentheses anymore. Now it says true and false. What is the truth value of a statement that is true and false? Well, that is false. And again, we know from the second row in our conjunction table, true and false is false. Okay, so this would be the truth value of that compound statement. Now, if you've done this a few times, you may be able to determine this in the very first step. Because if you come back up here and you look at this and you see, okay, I know I'm supposed to do all of this stuff in the parentheses first. But at the end of the day, once I've worked out everything within these parentheses, the end result of whatever's on the left side of this conjunction is either going to be true or it's going to be false. It's going to be one of those two things. Regardless of which one it comes out to, anytime I have a conjunction with one of my statements being false, the result is always false, like we got here. So at the end of the day, it didn't matter whether this statement was true or false because since I was making a conjunction with this statement and a false statement, the answer was going to be false no matter what. Okay, but it's good to see the entire process and write out all of these steps so you can see how this would normally work. Let's try some similar examples, but this time let's work with actual statements. So this time, P is going to represent the statement 4/10 equals 2/5. Q is the statement 15 is less than or equal to 9. And R is the statement the quotient of 125 and 25 is a whole number. And we want to determine the truth value of a couple of examples here, two statements that were given. So before we could do any of that, we're gonna work through this example basically the same way that we did this one, but now it's up to us to determine the truth values of P, Q, and R. We're not told whether they're true or false this time. We have to figure that out. So P, is P true or is P false? Well, 4/10 is equal to 2/5, and that's easy to verify because if you simplify this fraction, you'll end up with this fraction. So yeah, P is true. Q, is Q true or is Q false? Well, 15 is not less than or equal to 9, as this is stating, so it must be the case that Q is a false statement. What about R? The statement that says the quotient of 125 and 25 is a whole number. Quotient means you're looking at a division problem, and you divide in the order that these numbers are written. 125 divided by 25. Is that a whole number, or do we get some kind of a fraction out of that? 125 divided by 25 is just 5, and 5 is a whole number. So that would mean that the statement R is true. So P, Q, and R will be true, false, and true, respectively. So now let's use those as substitutions in each of these compound statements to determine the truth value. Okay? What is the truth value of not P or R? By the way, if you wanted to write this in words, now that we have actual statements up here, this would say that 4/10 is not equal to 2/5 because it's the negation of P, or the quotient of 125 and 25 is a whole number. That would be like in words what this symbolic statement represents. But we're not asked to translate it. We just need a truth value. So let's substitute in the truth values. From what we just said, P and R are both true statements in this description up here. So that means not P is going to look like not true, or R we know is also true. Okay? Not true or true. Well, not true means false. Okay? And in a disjunction, as long as at least one of the two component statements are true, the whole thing will result in a true. So this gives us a truth value of true. That one was pretty straightforward to evaluate. Didn't take a whole lot of work. This next one looks a little bit more involved. So let's give this one a shot. This one says P or not Q. Notice that it's in parentheses. And another compound statement, not P or R. So this one's pretty complicated compared to the last one, but it's the same approach. Substitute in your truth values. So P, we said that would be true, or not Q. Q, we said, was a false statement. So that's what that first set of parentheses looks like when making those substitutions. And, okay, P was true, so now we're going to say not true. Okay, or R, which we said was true. All right. Well, there's a couple of steps here. What I'm going to do is work out both sets of parentheses in this same step. True or not false. Actually, let's deal with the negation first, and then we'll work out the rest of the stuff in the parentheses. This would say true or not true. And not true or sorry. Back that up. That's incorrect. True or not false. Not false is the same thing as true. So this is true or true. And not true means false. So let's deal with that. Or true. Okay, so I've dealt with the two negations in this next step right here. Now what I want to do is work out both sets of parentheses. Notice that in both sets of parentheses, I have a disjunction. an or statement. And in each one of those, as long as at least one statement is true, then the entire disjunction will be true. So, at least one of these two statements is true. It turns out that both of them are true, but all we need is at least one. So that means that this first statement here is a true statement. And here we have a false statement and a true statement, but they're joined by a disjunction. And again, as long as one of them, at least one, is true, then the entire disjunction will be true. That's what we have there. Finally, we have a conjunction here, and. True and true. Remember, the only way that a conjunction can be true is if both component statements are true, which is what we have in this case. So we have another truth value of true. Okay? Somebody should count how many times I say the word true and false in this lecture. It gets a little repetitive. Okay, I think this is a good place to stop this first video. We'll start looking at constructing entire truth tables on our own in the next video.